In this presentation, I'll walk you through a biomedical signal processing system, specifically a heartbeat acquisition system. This system detects and amplifies heartbeat signals using a biosensor, the electret microphone, and a multi-stage analog circuit. Since heartbeat signals are weak and often affected by noise, the system processes them step by step, first capturing, then amplifying, filtering, and finally preparing them for output. This converts a raw biological signal into a clean, usable form that can be measured, analyzed, or connected to external devices. I will be explaining its schematic in four main stages, which are the preamplifier, inverting amplifier, a Sallen-Key second-order low-pass filter, and lastly, the audio amplifier or line-out gain control. In stage 1, from TP1 to TP2 is our preamplifier. It is the system's primary role to pick up the heartbeat sound from the stethoscope and amplify it to a usable level. Signal passes through C1, which is a DC blocking capacitor, allowing only AC heartbeat signal to pass while blocking DC components. A 10 microfarad capacitor is chosen to ensure even low-frequency heartbeat signals between 20 to 200 Hz passes through without significant attenuation. R5 and R6 form a voltage divider from VCC, which biases the non-inverting input of the op-amp to VCC divided by 2, since R5 and R6 are equal, giving us 4.5 volts. This is essential because the op-amp is powered by a single supply, needing to raise the reference voltage to the middle of the supply range so that AC signal can swing both positive and negative, ensuring that even though the op-amp has no negative supply, it can still process the full waveform. IC1A is a TL072 that is a dual low noise, high impedance JFET input op-amp. It's configured as a non-inverting amplifier, which amplifies signal picked up by the microphone. The op-amp's low noise ensures even small signals like heartbeats are amplified without adding significant noise. R2 and R3 resistors set the gain of the non-inverting amplifier. The gain can be calculated with the formula 1 plus R2 over R3 coming from the general non-inverting gain formula, which is equals to 23. The gain tells us how much the weak heartbeat signal from the microphone is amplified before moving to the next stage. Capacitor C2 is in parallel with R2, forming a low-pass filter that controls the amplifier's frequency response, ensuring that high-frequency noise is filtered out. On the other hand, C3 is in series with R3, forming a high-pass filter, allowing high frequency to pass and blocking out low-frequency signals. Together, capacitor C2 and C3 and resistors R2 and R3 form a band-pass filter, meaning the circuit only allows signals within a specific range to pass through. Lastly, C4 acts as the output coupling capacitor to block DC bias from reaching the next stage, ensuring only the AC heartbeat signal passes through. This allows the signal to be centered correctly for the subsequent processing stage. Onto my measurement process, I connected the oscilloscope probes, one at TP1 and the other at TP2. Next, I applied 9 volts power supply to my circuit. Then, I set the function generator to output a 200 mV peak-to-peak sine wave at 200 Hz. At TP1, channel 1, the oscilloscope shows a sine wave with 208 mV peak-to-peak, slightly higher than 200 mV input, but this small difference is due to component tolerances and is still an acceptable range. This confirms that the DC blocking capacitor C1 is correctly passing the AC signal without any noticeable attenuation. At TP2, channel 2, the oscilloscope shows a sine wave with 4.72 volts peak-to-peak, which is a strong, clean, and in-phase signal. This confirms the non-inverting amplifier is functioning correctly with proper gain and DC biasing, since the output remains centered around VCC divided by 2, with no clipping due to voltage divider biasing. Finally, I tested the same 200 mV peak-to-peak input at 1 kHz. At TP1, the input remained at 208 mV peak-to-peak, and at TP2, the output dropped to 3.52 volts peak-to-peak. This reduced gain is expected since low-pass filter, C2 with R2, attenuates higher frequencies like 1 kHz, showing that the filter is working correctly. In stage 2, from TP2 to TP3, is our inverting amplifier. Its role is to further amplify stage 1 so that it's strong enough for the filter in stage 3 to clean up effectively, this time with adjustable gain and an inverted output. IC1B is the second op-amp inside the TL072 dual op-amp chip, the same one used in stage 1. It's configured as an inverting amplifier using negative feedback. This means that when the positive half cycle of the input enters the inverting terminal, the output produces a negative half cycle, or vice versa, resulting in the entire waveform being inverted and becoming 180 degrees out of phase with the input. A portion of the output is fed back to the inverting input through the 100 k ohms potentiometer, forming a resistor network R4. R4 is a fixed resistor placed between the input signal at TP2 and the inverting input of the op-amp. Its role is to control how much of the input signal is fed into the op-amp. It sets a stable input impedance, ensuring consistent signal loading from the previous stage. As the signal enters through R4 into the inverting input, it sets the input impedance alongside the feedback resistor P1 to determine the gain of the amplifier. P1 is a 100 k ohms potentiometer, which is placed in the feedback loop between the op-amp's output and its inverting input. The formula for the voltage gain for closed-loop inverting op-amp is AV equal to minus RF over RIN, and according to my circuit, is negative P1 over R4, giving me negative 10. The negative sign shows that this is an inverting amplifier, meaning the output signal will be 180 degrees out of phase with the input. We can change its resistance by adjusting the knob, and this adjustability is useful in preventing clipping or distortion. As in stage 1, R9 and R10 form a voltage divider that biases the non-inverting input at VCC divided by 2, allowing the op-amp to handle AC signals properly with a single power supply. I connected channel 1 to TP2, which is my input, and channel 2 to TP3, which is my output, while I kept the power supply at 9 volts and set the function generator to 200 mV peak to peak at 200 Hz. The output waveform was a clean, amplified and inverted sine wave as expected from an inverting amplifier with a voltage of 4.16 volts peak to peak, while my input has a voltage of 4 volts peak to peak. The phase inversion happens because the op-amp uses negative feedback to hold the inverting input virtually equal. The slight gain increase confirms the potentiometer was set for moderate amplification to achieve my desired gain to ensure the waveform is clean, undistorted, and noise-free heartbeat waveform. Adjusting the potentiometer, I can control the output amplitude and prevent clipping and distortion, which is critical when amplifying delicate biomedical signals like heartbeats. I then changed the input frequency to 1 kHz, keeping amplitude and connections the same. The output was still inverted, but the amplitude was lower of 3.20 volts peak to peak, while my input was 3.12 volts peak to peak, as factors like op-amp bandwidth or a lower potentiometer setting can reduce gain at higher frequencies. In stage 3, from TP3 to TP4, uses a Salon-Key second-order low-pass filter. Its main role is to clean up the signal by allowing low-frequency heartbeat waveforms to pass through while attenuating unwanted high-frequency noise. By filtering before amplification, this stage ensures only relevant signal reaches the output, preserving clarity and heartbeat accuracy. The stage begins with C5 and ends with C8, both acting as coupling capacitors. They block DC voltage while allowing AC signals to pass, preventing DC offsets from previous or following stages from affecting waveform integrity. R11 and R12 form a voltage divider that provides a reference voltage of VCC divided by 2 to the non-inverting input of the op-amp. It is the same principle used in earlier stages to allow the signal to swing around mid-supply in a single supply design. C6 is a filter capacitor that forms the core of the filtering function. The filter's behavior is mainly shaped by R7, R8, C6, and C7, which form the two RC networks. Together, they define the cutoff frequency, Fc, using the formula Fc equals to 1 over 2 pi multiplied by square root R7, R8, C6, and C7. This formula applies because the salient key configuration uses two RC networks. Subbing in the respective values of resistors R7 and R8 and capacitors C6 and C7, the cutoff frequency was calculated to be around 1.023 kHz. This ensures only frequencies below 1.023 kHz passes through cleanly, while frequencies higher than 1.023 kHz are increasingly attenuated. IC2A uses a second IC TL702 and is configured in a non-inverting salient key topology. This setup filters the signal while also inverting it again. Since stage 2 already inverted the signal, stage 3 brings it back in phase with the original input. This is important for a clean audio playback and compatibility with the final output stage. Capacitor C7 is placed in the feedback loop. It shapes the frequency response of the filter by controlling how much high-frequency energy is fed back into the input. At low frequencies, C7 has little effect and the op-amp behaves normally, but at high frequencies, C7 acts like a short circuit in the feedback loop, reducing gain and suppressing noise. I connected channel 1 to TP3, which is my input, and channel 2 to TP4, which is my output, and the power supply as well as the function generator is set the same as the previous stages. On the oscilloscope, I measured 4 volts peak to peak at TP3 and 3.76 volts peak to peak at TP4, with both waveforms perfectly in phase. This small difference in amplitude indicates the circuit is operating near unity gain at 200 Hz. Unity gain means the output is nearly equal to the input, and this result is expected since 200 Hz is below the filter's cutoff frequency of 1.023 Hz. Next, I tested the circuit with a different frequency of 1 kHz. The signal at TP3 measured 2.88 volts peak to peak, while at TP4 it dropped significantly to 1.36 volts peak to peak. This sharp reduction is ideal since 1 kHz is close to the cutoff frequency, causing RC networks and C7 to begin attenuating the signal more aggressively. This demonstrates the second-order filter response, which rolls off higher frequency at about -40 dB per decade. The op-amp's gain bandwidth limitations also reduce its responsiveness at higher frequencies, contributing further to attenuation. Together, these effects ensure only the important low-frequency components, like heartbeat, are preserved while higher frequency noise is effectively removed. Finally, in stage 4, from TP4 to TP5, serves as the audio amplifier or line-out gain control. Its role is to boost the clean signal so it can drive the external speakers, allowing us to clearly hear the heartbeat. Although stage 3 has already filtered the signal, it is still too weak for audio playback. That's where stage 4 comes in, combining the LM386N1 audio amplifier with a potentiometer to boost the signal and let us manually control the volume, ensuring a clear, distortion-free output. The input signal enters port E of the potentiometer P2 and exits through port S, which leads into the LM386 amplifier. P2 acts as a volume control, where turning the knob clockwise decreases resistance and allows more signal into the amplifier, increasing volume. Turning it counterclockwise increases resistance, reducing volume. This provides fine control over audio loudness, which help prevent distortion or discomfort during playback. The core of this stage is the LM386N1, a low-voltage audio amplifier powered by a single 9-volt supply. It's ideal for biomedical systems due to its lower power consumption and ability to drive speakers effectively. In this configuration, pin 2 and pin 4 are grounded, with pin 2 being the inverting input and pin 4 the ground reference. This stabilizes the amplifier in non-inverting mode. Between pin 5 and ground, we have R17 and C15 forming a Zobel network. This stabilizes the amplifier and prevents high-frequency oscillation caused by the inductive nature of speakers. The capacitor provides a path to ground for high frequencies while the resistor dampens the current together, creating a balanced, loud and clean output. C15 also connects across pins 1 and 8 of the LM386N1. According to the datasheet, since the two pins are specifically designed for gain control, increasing the internal gain from 20 times up to 200 times. This gain boost is critical for amplifying very weak heartbeat signals into an audible range. Lastly, C13, the large output coupling capacitor, blocks DC voltage from reaching the speakers, which allows only the AC waveform to pass through. This prevents potential pops, distortion, or long-term damage to audio equipment, ensuring the heartbeat signal remains clean and safe to listen to. I connected channel 1 to TP4, which is my input, and channel 2 to TP5, which is my output, and the power supply as well as the function generator is set the same as the previous stages. At TP4, the signal measured 1.64 volts peak to peak, and at TP5, the output jumped to 7 volts peak to peak with both waveforms perfectly in phase. This confirms that the LM386 amplifier is working correctly. Since 200 Hz is well below the cutoff of the previous low-pass filter, the signal entered this stage clean and strong. The LM386 amplified it efficiently to an audio-appropriate level, and I used the potentiometer to adjust volume and avoid clipping or distortion. Next, I tested the circuit using a 1 kHz sine wave. At TP4, the signal dropped to 720 mV peak to peak, and at TP5, it was 2.88 volts peak to peak. This smaller output came about because 1 kHz lies closely to the cutoff frequency of stage 3. The input signal had already been attenuated before reaching stage 4. Since the LM386 amplifies proportionally, a weaker input produces a smaller output. It means only low-frequency components like heartbeats are emphasized while high-frequency noise remains suppressed. To summarize, this heartbeat acquisition system successfully detects and amplifies heartbeat signals through a well-designed multi-stage analog circuit. It starts with a microphone capturing subtle air pressure changes, followed by preamplification and DC biasing. The signal is further amplified and cleaned using a low-pass filter to remove high-frequency noise, preserving the low-frequency components of the heartbeat. Finally, an audio amplifier boosts the signal to a level suitable for real-time monitoring through speakers. Each stage plays a vital role in ensuring the output is clear, undistorted, and accurate, demonstrating the system's effectiveness in biosignal acquisition and processing.